All right, now, so I said that what you want as a search engine is you want your index to be relatively fresh, right? It's not useful to your users if your pages are, if the page in the index is as it was 2 years ago and it's changed 100 times since then. So what you want is you want to keep your index fresh, and the basic decision there is you have to figure out how often should you recrawl a particular page. So how do you define the freshness of your index? So you could just define the freshness of the web page as sort of a binary variable, right? So a page is either fresh or stale, right? A stale page means that you have a copy in your index and the page has changed since then, right? So you don't have the most recent copy. And fresh just means that the copy that you have is the most recent copy. There is nothing more recent there. So freshness is a binary variable. So you could try to just maximize the freshness of pages over your entire index. This is slightly problematic. First of all, how do you get that? And second, if you were able to get that, this doesn't indicate a degree of freshness or staleness, right? So a page could have been indexed a month ago or a minute ago and it's still stale. So that's not a very good metric. So what else could you do? What you could do is you could minimize the age, the expected age of your entire index. So what is the age? Age is basically a number of days that the page has been stale. So if you have time on the x-axis, like the green lines represent your crawl times, this is when you have visited a particular page. Red lines represent the updates. Freshness is just a binary function, right? So it was stale, and then I crawled it at this point, so now it's fresh. And it's been fresh until the next update, and then freshness goes back to 0, and so you get a step function. For age, what's happening is I've crawled it. The age stays 0 until the next update to the page, until the time when the page changes, and then it goes linearly until I get to the next crawl time, and then it drops back to 0, right? So I have 2 updates that happen in this region, but that doesn't affect the age, because the age starts growing once you've had the first update to the page. Once it's become stale, right there, the age starts growing, and it's not affected by subsequent updates. So what you want to do is you want to estimate an age for each page, and then use that age as the priority for your crawler. Right? So, and it's not really the age itself, it's a combination, but that's the basic idea, right? So what you want to do is you want to crawl the pages that you think, that you're most confident have changed. Since you last crawled them. Okay. So the problem, of course, is you don't know if the page has changed or not, right? So this age graph, it's a nice thing if you know when the update has happened. But of course, you don't know that when the update happens, because whoever changes that page is not going to send you an email saying, oh, by the way, I've changed that URL. So it doesn't work that way. So you don't know when the pages have changed, but you can make some assumptions about the changes, and then do something based on those assumptions, right? So the assumptions that are typically made about page changes are that page changes are independent of each other, right? So that's a big assumption, but you really have to assume it if you have to go if you have to go somewhere. But if you don't assume it, you can't really do anything. And the second assumption that you make is you can't have 2 changes happening simultaneously, right? So if there's 2 changes, there's at least a millisecond between them. Right? They won't happen at the same instant in time. Now, once you make those 2 assumptions, what you know is that the page updates will be a Poisson process. Right? So a Poisson process is basically a process that says that these updates are going to have an exponential inter-arrival time. The arrival time, the time between 2 updates will follow an exponential distribution with some unknown parameter. Right? So they could happen frequently or infrequently, that's what the parameter determines, but the updates themselves will be exponentially distributed. Now, once you know that, you could construct an expected age of the page. So let's look at what this is doing. Right? So suppose that I have crawled this page before, right? And I'm going to set the time of 0 to correspond to the time when I've crawled it last. Right? So suppose I haven't crawled it for t days. Right? What I want to know is what is the expected age of this page. So the way I can compute that, of course, I can't determine that, but I can estimate it. Right? So integrals sometimes are confusing, so maybe think of it as a summation, right? So I'm gonna sum up over different. X is gonna represent the day number since I've last crawled it, right? So X is gonna go from 0, day 1, day 2, day 3, all the way up to day number t, right? So now, if the page was first modified on day X, what is the age? What would be the age of the page now? T minus x, right? Because now it's time t, it was modified on day x, so the age has to be t minus x, and it doesn't matter how many times it's been changed. The only thing that matters is that the first change was on day number x. So this would be the age if the change occurred on day x. And of course, I don't know if the change occurred on day x, but what I know is that the amount of time between the changes is exponentially distributed if I can make those two assumptions. So the probability that the first change came on day x is exactly the probability of inter-arrival time in a Poisson process. And that is an exponential distribution with some parameters. So it's going to have this form, c times e to the minus cx, where c is the parameter that tells you sort of what is the true update rate for that page. How often does it get updated? And of course you don't know c. But if you did somehow know c, what you could do is you could now compute the expected age of the page by integrating over all possible x's, saying, what's the chance that the change happened on day 1, right? And then it's t minus 1 is the age. What's the chance that it happened on day 2? And then it's t minus 2 is the age. And then you integrate it and you get the expected value. So that's the expected age of the page. And I guess here's an example. So if you know that the page changes once every 7 days and you haven't crawled it for 7 days, then it's not 7 days old, the expected age. It's not 3.5 days old, as the naive estimate might say. It's actually on average going to be 2.6 days old in a situation like that. Right? So it's not half of t. It's actually smaller than t. See, it's sublinear growth. Okay, so that's all fine and dandy. If you know C, and of course no page is going to say, here's my true frequency of updates. So how do you get C? And the idea is, if you have certain pages that you are crawling frequently for whatever reason, you should actually try to learn C, and it's not particularly difficult. So let's see how would you be able to learn the rate of update for a particular page. So now. If it is a Poisson process, it's actually pretty easy to estimate C. What you need to do is you need to sample things and just count how many times the page was changed. So suppose I crawled the page at intervals delta t1, delta t2, delta t3, right? And during each one of those intervals, Ci was the number of changes during the interval, right? So if I had that, so then the maximum likelihood estimate for C is just the sum of the Ci's divided by the sum of the delta T's. Right? So you count the total number of changes in your sampling time, right? And then divided by the length of the sampling time. And that's going to be an unbiased estimate of the sampling rate. So that's nice, and you could do it, but there is a big problem. The big problem is you don't actually know Ci. Right? When you crawl the page, say I've crawled it 5 days ago and now I crawl it again, and I see that the page, say the page hasn't changed. In that case, I know that CI is 0, right? There was 0 updates to the page. Or there could have been actually updates, but they canceled out, right? So it doesn't actually matter, right? So you know when CI is 0. But if the page has changed, the only thing you know is that it has changed. You don't know how many times it's changed in that interval. So you basically know if it's 0 or if it's non-zero. So if you just put 1s instead of all CIs, you're going to be underestimating the rate of change for the page. So how can you fix that? Well, you could try to make the deltas very, very small, right? Basically so small that either CI is 1 or 0, but that of course is a lot of wasted crawling effort. You could do it, a better way would be to do it adaptively, right? So what's a way to do it adaptively? You set your delta t to some value, and then every time you crawl a page, if the page has changed since your last crawl, you make delta t a little bit smaller, right? And if it hasn't changed, you make delta t a little bit larger. So what that'll do is, if you keep crawling it and the page keeps changing, you'll start crawling it faster and faster and faster and faster and faster, right? And eventually you'll get to so with something like that, if you increase and decrease by the same epsilon, you'll reach an equilibrium where about half the time the page will have changed, and half the time it will be the same as the last time you've crawled it. So basically that would allow you to get to some reasonable crawl frequency for a particular page. Okay. So that's how you would normally set the priorities. But of course, you could have other goals in mind. So you could build focused crawlers that instead of trying to keep an index up to date over over the entire web or over the entire subnet, you might be interested in a particular topic. And then your priorities basically become the probability that that URL discusses that topic, and then you can estimate it in all sorts of ways. I'm not actually going to spend time on that.